Hi everybody! So in today's video we're going to be talking about another application of derivatives, which is that we can use a linear approximation, which is really another name for a tangent line. So we can use a linearization, which is a tangent line, to approximate, which means estimate, y values of a function. So here's an example of why we might need to do this. So if I've got f of x equals x squared, and I want to find the value of f of 2 and f of 2.1, what that means I need to do is take my original equation and plug in the number 2. Which means I would have 2 squared, which is 4. So finding f of 2 is relatively straightforward. However, finding f of 2.1 is a little bit more complex. In order to find f of 2.1, I don't know about you, but I don't happen to know the value of 2.1 squared off the top of my head. So I would definitely need to use a calculator here, which is what I'm going to do. I'm going to type this in on my calculator, and it gives me 4.41. So this is a value that I would need my calculator for. And this is a value where I did not need a calculator. The idea of today is that we are going to be able to estimate with relatively good accuracy these values for which we would normally need a calculator without using a calculator. And the way we're going to do that is we're going to use a tangent line. Since a tangent line stays very close to the graph of the original function, when it is close or near the value at which it is tangent, we can use tangent lines to estimate function values. When we do that, we call our estimate a linear approximation because we are using a line to do our estimate. This process is called creating a linearization. And the word linearization is just another word for tangent line. But we're going to rearrange the equation a little bit to make it look a little bit more useful for estimating values. Another way we could say this is that we are using a linear approximation. So if I say linearization or if I say linear approximation, those two things mean the same thing. In a visual representation, if a problem says let f of x equal x squared, write the equation of the line that is tangent to f of x at x equals 2. Then approximate the value of f of 2.1. Visually, here's what's happening. We're looking at the graph of f of x equals x squared. So I'm going to graph that right now. X squared goes through 1, 1, 2, 4, negative 1, 1, negative 2, 4. So x squared would look like this. Now, just like in our beginning up here, finding the value of f of 2 we can do without a calculator. So we're going to draw our tangent line at x equals 2 because that's a value that is relatively easy to find. So I'm going to draw my tangent line where it connects to the graph. It brushes this graph when x is 2. So that's going to look like this. What we're going to do next is we're going to use this tangent line to approximate what's happening when x is 2.1. So my tangent line is at x equals 2, but we're using it to estimate what's happening at 2.1. Now 2.1 would be here. So if I go up and I find where it connects to the tangent line, it would be like here. You'll notice that at this point, the blue tangent line is very close to the purple curve. So the y values that I get using the blue tangent line will be very close to the y values that would be on the purple curve, because those two graphs are very close together, since the tangent line is very close to the curve in the area at which it is tangent. Now the farther away we get, so if I went to like where x is, I don't know, 4, the blue line would be much farther from the purple curve. So we want to use, like if we want to find 2.1, we want to use a number close to there, but that's easy to calculate, like 2. If we want to find 2.1, we're not going to use 4. Now this is a visual representation of our idea, but our algebraic representation works like this. Anytime it says in the problem, write the equation of the line that is tangent to f of x at x equals 2, then approximate the value of f of 2.1. Anytime it says in the problem, use a tangent line to approximate a value, that is your clue that we're going to need something called a linearization. So that vocabulary is going to come up a lot. Use the tangent line to find an approximation, or write the tangent line to find an approximation. As soon as you see those words, you know we need a linearization. So what do? Well, we're going to start by writing our tangent line. In order to write the equation of a tangent line, we always start with a list. We're going to need a point. We're going to need a slope. And that's going to allow us to write our tangent. The point that we're going to use is going to have an x value of 2. So in my ordered pair, the x value would be 2. In order to calculate the y value, I'm going to take the 2 and plug it in to the original equation, because this tells me my outputs are always my inputs squared. So to figure out the y value, I would do 2 squared, which is 4. In order to find the slope of a tangent line, we use the derivative. So I would start by finding the derivative of f, which would be 2x, and then I would find the derivative and I would plug in that number 2 again, which means I would get 2 times 2, which is 4. So my slope would be 4. Once I have a point and I have a slope, I can combine those to write the equation of the tangent line. So I would write y minus 4 equals 4 parentheses x minus 2. And normally that's where we would stop. However, we want to use this line to estimate a new y value. In order to do that, the y in this equation needs to be by itself. So what we're going to do now is we're going to rearrange the tangent line to create what's called the linearization. So we're going to add this 4 to the other side in order to get the y by itself. So my new equation would look like this. Y equals 4 parentheses x minus 2, and then plus 4. And then, and this is the part that's just a notational thing that you need to be aware of, because we're using this to estimate values of f, we're going to change y into f of x, and we're going to say is approximately equal to, and then we're going to say 4 parentheses x minus 2 plus 4. So we're changing the y to f of x because we're using this equation to estimate values of f of x. So what we're saying is that these y values are approximately the y values of f. Finally, if I want to know what's happening when we plug in 2.1, I'm going to take this 2.1 and I'm going to plug it in for the x value in this new equation. So my new equation would be f of 2.1 is approximately 4 times 2.1 minus 2 plus 4. 2.1 minus 2 is 0.1. 4 times 0.1 is 0.4, which, if I simplify that, is 4.4. So we're estimating that 2.1, if I plug it into here, 2.1 squared, is approximately 4.4. Now, if we look back at what we calculated a few minutes ago, using a calculator, we got 4.41. So our estimate is actually pretty close to our actual value. We just didn't need to use a calculator to get it. Let's take a look at a few more examples. So in this next problem, it says, let f be a function that is differentiable for all real numbers. That means we can take the derivative. The table above gives values of f and its derivative between negative 1.5 and positive 1.5. The second derivative has the property that the second derivative is always greater than 0 between negative 1.5 and positive 1.5. For problem number 1, it says, write an equation of the line tangent to the graph of f at the point where x is 1. Use this line to approximate the value of f of 1.2. As soon as I see that we're writing the equation of a line that is tangent and we're going to use it to approximate a value, it tells me I need a linearization. So I'm going to start by figuring out a point and a slope and writing my tangent line. Now the point is going to be at the place where x is 1. So my ordered pair is going to have a 1 for the x value. In order to find the y value, I'm going to look in the chart at where x is 1, and I'm going to find the value of f of x, which is negative 4. In order to find the slope, I'm once again going to use the chart. So when x is 1, the slope is 5. So I would have 5 for my slope. Therefore, my tangent line would be y plus 4 equals 5 parentheses x minus 1. So I've done part 1 of this question. Write an equation of the line that is tangent where x is 1. The second part of this question says use this to approximate the value of f of 1.2. So what we're going to do now is create the linearization. All that I'm going to do is rearrange this equation a little bit. So I'm going to subtract the 4 on both sides, which means I'm going to have y equals 5 parentheses x minus 1 and then minus 4. And then I'm going to change the y to f of x because we're going to be using this equation to approximate values of f of x. So I would say f of x is going to be approximately 5 parentheses x minus 1 minus 4. Finally, I'm going to plug the number 1.2 into this x. So I would have f of 1.2 is approximately equal to 5 parentheses 1.2 minus 1 and then the minus 4. Now 1.2 minus 1 is 0.2. 5 times 0.2 is 1, and 1 minus 4 is negative 3. So f of 1.2 would be approximately negative 3. Let's take a look then. We'll skip number 2. We'll maybe talk about that in class if we need another example tomorrow. And let's take a look at using accuracy. So one of the things we need to think about whenever we're approximating something is whether the estimate that we have is an overestimate, which means it's too big, or an underestimate, which means it's too small. We can figure this out by looking at the concavity or the curvature of the function. This curvature is called the concavity, and it can be determined by looking at the second derivative. So we're going to look at the second derivative of our function. If your second derivative is greater than 0, which means it's positive, then we know that the curvature of the function is up. So we say that this curves up, which we call concave up, which we say looks like a cup. So whenever your concavity, your second derivative, is positive, your graph looks like a cup. It's always curved up. When that happens, all of your tangent lines will always be below the curve. So all of our estimates will be underestimates. They're all going to be below the real number. Whenever your function has a second derivative that is less than 0, which means that it's negative, we say that it curves down. In other words, it's concave down. Now, I like to think about this as curving down is like a frown. Whenever your function is a negative second derivative, it curves down like a frown. So if you draw your tangent lines, they're all above the curve, which means all of your estimates will be overestimates. Now, how do we use this? Well, let's go back to the problem we just did. This is the exact same example we just did, and it says, write an equation of the line that's tangent, use this line to approximate the value of f of 1.2, but this is the part we're going to focus on now. Is the estimate an overestimate or an underestimate? Justify your answer. Now, we didn't talk about this before, but we did figure out before that the approximate value of 1.2 was -3, which we did on the other problem. What we're going to do now is look back at something very important that was actually in the instructions. In the instructions, it told us that the second derivative is greater than 0. That means that it's positive. If your second derivative is positive, and I would always draw this on my paper, I would never try to memorize this, then my graph is concave up like a cup. So all of my tangent lines are below the curve. So I would write the estimate is an underestimate because, and here's your reason, the second derivative is greater than 0. All right, that's it. Thank you guys so much for watching. Have a wonderful afternoon, and I will see you for some practice tomorrow.